So like I said, every example we've seen so far has had each x-intercept appear once. We're going to look at some examples of what happens when an x-intercept appears more than once. And what we're going to use for a word for this is something called multiplicity. So if we think of a basic parabola that you have graphed before, if I was going to get you to graph y equals x minus 1 squared, using our transformations unit, that's just a parabola moved 1 unit to the right. And so the graph of that parabola looks like this. It still has an x-intercept. That x-intercept is at 1. But instead of going through that x-intercept like our cubic graphs have been doing, it bounces off of that point. And we say that that x-intercept, because when it's factored, it's really appearing twice, right? It's the same factor twice. So we would say that the x-intercept of x equals 1 is a root that has a multiplicity of 2. And we use the word multiplicity because it happens more than once. And in this case, it happens twice. So what we're going to look at is what happens to graphs when a root has a multiplicity of something bigger than 1. Because all of our ones so far have only had a multiplicity of 1, and then our graph just goes straight through that point. But when it has a multiplicity of 2 or a multiplicity of 3 or 4 or 5, we're kind of curious what happens to that. So here is the graph of x cubed minus 3x squared plus 3x minus 1, which can be factored to be x minus 1 cubed. Again, if you think about your transformations unit, what would x minus 1 cubed look like? Well, it'd be an x cubed graph moved 1 to the right. And what does an x cubed graph moved 1 to the right look like? It looks like this. So now we have an x-intercept. It has a multiplicity of 3. And at our x-intercept, instead of going straight through, it bends as it goes through. So those are those two graphs. What I would like you to do is off to the side here, we're going to add some notes. And our notes off to the side can be separated by when a root has a multiplicity that's even. In other words, something like 2, 4, 6, 8, and so on. When your multiplicity is even, what happens on the graph? And these are not mathematical terms, it's just describing what happens. The graph bounces off the x-intercept. So just like a parabola, like that x minus 1, right here is our x-intercept, but instead of going through the x-axis, it bounces off of it and goes back up again. So anytime we have an even multiplicity, and it doesn't matter which even number it is, it'll always bounce off of that. Now when we have an odd multiplicity, so that is any number like 1, 3, 5, 7, and so on. Anytime we have an odd multiplicity, the graph will go through the x-axis. And we have two situations. If the odd multiplicity is a 1, it just goes straight through. Those are all the examples we've done before. We just drew our line straight through that x-intercept, no problem. But we're going to find out that any time it is bigger than 1, like 3, 5, 7, and so on, our graph is going to go through, but it's going to bend as it goes through. Just like an x cubed graph has a bend. It bends so much that the graph actually gets flat. I don't know if you've ever noticed that on an x cubed graph. It bends so much that the graph actually gets flat. Later on in calculus, you're going to even find out that it changes something called concavity. So later on when you take calculus, you're going to learn that this part of your graph is concave down because the bend is like that. And this part of your graph is concave up because the bend of the graph is like that. So at these odd multiplicities where it goes through, but it's a higher power, it's going to bend. Yes. So we have, when something is factored, now we're going to add thinking about the multiplicity of that graph. So in our example here, on example 3, we're going to sketch these graphs. The nice thing about these ones is they're already factored. So we're not going to have to worry about factoring them. We can use the same intercepts technique. So let's find our y-intercept. Y-intercept's really easy. You just plug 0 in for x. It's going to equal, well, when I plug in 0 for x, the first factor is going to be 1, 1 to the power 4. Second factor is -2. When I multiply that all out, I have a y-intercept at -2. When I want to find my x-intercepts, that's when I make y equal to 0. So I'd have 0 equals x plus 1 to the 4 times x minus 2. Well, I'm going to get x equals -1 and x equals 2. But underneath these, I'm going to say this one has a multiplicity of 4, because my exponent is a 4. This one has a multiplicity of 1. So this is where we use that idea of odd and even multiplicities. The multiplicity of 4 means that it's going to have to bounce off the x-intercept. And a multiplicity of 1 means the graph is going to go straight through. The other thing we need to know when we graph this is the end behavior. The end behavior is by finding out what kind of graph is this. If you multiplied this all out, would this be an x cubed, x4, x5, x6? How do you tell? It's going to be an x to the 5 because this first one happens 4 times. So you imagine x times x times x times x 4 times. And then you're multiplying by another x in the last one. You're going to get an x to the 5. Now, how do I know if the leading coefficient is going to be positive or negative? Well, since all my x's are positive in the first one and all my x's are positive in the second one, we're going to get a positive x to the 5 graph, which means since it's odd, it's going to act like a line. Since it's positive, it's going to act like a positive line with a positive slope. So now we know what our end behavior looks like. So we know our end behavior, we know our x-intercepts and our y-intercepts. We put them all on here, so we have x-intercepts of -1 and +2, our y-intercept of -2, and we know that it acts like a positive line. At the one x-intercept, it's going to bounce. At the other x-intercept, it's going to go straight through. So we need to, our end behavior says start from down here. We need to bounce, go through, bounce, and then go through our second one. A y-intercept, it'll always go through there. Notice how, in order to graph the curve smoothly, I made my minimum a little bit lower than that y-intercept. That's fine. If you made your minimum your y-intercept, they wouldn't take off marks for that because we don't know how to figure that out until we take calculus. Or you could type it into your graphing calculator and find the minimum from that as well. But this is an accurate sketch. Now I would still lose marks on this graph. Okay? I would lose marks on this graph because I have made ticky marks, but I haven't labeled. No one knows if this is going by 5s, going by 1s. I know that you get sort of typical that you're going by 1s, but you need to label something. So if I label this as -1 and that is 2, it becomes obvious that those are going by 1. But I would still lose a half a mark because I haven't defined my scale on my y-axis, so I would also need to label something on my y-axis as well. You need to have a scale to indicate what your graph means. IB courses, they even get fussy by labeling your axes, but you won't lose marks for not labeling your axes. If you don't put arrowheads on the end of your graphs, you would lose a half a mark for that. So we want to draw it as accurately as we can and as carefully as we can. So there's our first one with a multiplicity of 4 and a multiplicity of 1. In our next example, we can find our y-intercept to begin with by plugging in 0 for x. We're going to get a negative times 1 cubed times a -3. We're going to find out that our y-intercept is +3. To find our x-intercepts, here's where you make y equal to 0. So we get x could be 3 or x could be -1. In which case, this one has a multiplicity of 3. This one has a multiplicity of 1. So the multiplicity of 1, our graph is just going to go straight through. Our multiplicity of 3 is where we're going to have a bend and go through. Yeah. So what does this mean for a graph? Well, we can place all of our values on there. We need to have a -1 and a 3, so I'm going to make sure I label those. Those are my two x-intercepts. I know that at +3, I have my y-intercept. Looking at my original graph, what kind of graph is this one? It's going to be an x to the 4 graph. Is it going to be a positive x to the 4 graph or a negative x to the 4 graph? It's going to be a negative x to the 4 graph because we have x here, 3x's here, that gives me x cubed, and then a negative out in front, which would multiply that coefficient by a -1. So this is going to act like a parabola going down. So what does our final graph look like? Well, we know we have to start down here. So I'll draw that arrowhead. We know that at -1, we have to bend. And at +3, we're going to just go straight through. Okay? Sometimes I like to show the bend by starting on that point. And if you think about the graph changing from concave down to concave up at that point, it really shows the bend. It really shows that it flattens out there. So if you have your curve so that the curve is rounded down like a sad face and then rounded up afterwards as a happy face, then you can really show that bend well. And the other one at +3, because it has a multiplicity of 1, it just goes straight through. There's no bend there. So both of those x-intercepts, our graph went through the x-axis, but one of them had a bend and one of them went straight through. You're also going to find sometimes you're going to make mental math mistakes with your y-intercept. So if you know what the end behavior looks like and you know it's supposed to bend, and you bent at -1 and you know you have to keep going up and you had your y-intercept below, something's wrong. Either your end behavior is wrong, either your multiplicity is wrong, or your y-intercept is wrong. So then you'd have to go back and check your work. Don't make a new x-intercept to make it work. Don't bend your graph or bounce it instead of bend it. So it's telling you something went wrong and you need to check it. Okay, we're going to work on these till the end of class, 9 to 12.